There's an important distinction to make between cause and effect when analyzing the motion of objects. There are two very separate questions that we can ask. The first is, how does a particular object move? This is a purely descriptive, geometrical question that we're asking. What does the geometry of the motion look like? If we were to draw its trajectory as a function of time, what's the shape of that trajectory? The study of the geometry of motion of a trajectory is referred to as kinematics. The second question we can ask is, why does an object move the way it does? Why does the kinematic description of the trajectory look the way it does? This concerns what the causes are of the motion and of the changes in that motion. The study of the cause behind the changes of motion is called dynamics. Newton's second law of motion connects these two questions. When we write F equals ma, this is more than just a mathematical identity. Physically, we're connecting two very different questions. And we can symbolize that by dividing the equation into its two sides. The right-hand side, the ma side, is essentially asking the question of how. How does the object move? What does that motion look like? It's a description, a geometric description of the object's motion. The left-hand side of the equation, where the forces are, answers the question of why. Why does the object move the way it does? What causes the motion to change? These are very different conceptually, and the remarkable thing about Newton's second law, in fact, one of Newton's signature accomplishments, was to realize that these two questions can be connected in this way through Newton's second law of motion. Since these are very different issues, we'll examine them separately in our course. We'll begin this week by looking at kinematics in 1 and 2 dimensions, basically learning how to describe the geometric motion of an object and its trajectory. We'll follow that by discussing the dynamics of the motion, examining why an object's motion changes when forces are applied, through a discussion of Newton's laws and their applications.
Now that we've described the position vector of the runner, let's try to describe what happens in time as the runner moves along our road. Suppose at a later time our runner has gone down the road just a little bit, and so runner has moved a little bit. Remember, at time t, we described the position vector r of t was equal to the coordinate function. X is a function of time, I hat, and this distance here was our x of t. Now our position vector, a little bit later, so here we're at time t plus delta t. The runner has moved a little bit. And we'll now describe the position vector, because I don't want to overlap it. That center point is up here. It's going to point in this direction. And this is what we call r of t plus delta t. And that vector, r of t plus delta t, the coordinate function is no longer at time t, but t plus delta t, I hat. And we would now like to describe the displacement vector. So our next step is to describe the displacement vector for the interval t to t plus delta t. And that displacement vector is defined, we use the symbol delta r, and what we mean is the vector r of t plus delta t minus the vector r of t. Now what that vector corresponds to is the vector right here. This is our delta r. And if we now use our two definitions here, then this becomes x of t plus delta t minus x of t I hat. And this quantity here we refer to as the component of the displacement vector. So delta x is the component of the displacement vector. And as before, the component can be positive, which would correspond to the person moving a positive component, positive I hat direction, in the positive x direction, as shown in this figure. If the displacement vector is 0, the person could have run forward and come back, and at time t plus delta t be in exactly the same spot as time t. the displacement vector is 0 in that case. The displacement vector could have a component that's negative. And what negative means is at the end of this interval, t plus delta t, that the person is on to the left of the runner. And so this quantity would be negative. And so this is our crucial displacement vector that describes only the difference in positions between the person between time t plus delta t and time t. We would now like to begin our analysis of motion. And we'll start with one-dimensional motion. Let's just consider a person running along a road. And so here's our runner, and here's our road. And what we want to do is be able to describe the position, the velocity, the acceleration of this runner. In order to do that, we need our first mathematical tool, which is a coordinate system. What is a coordinate system? Well, the first thing that we want to choose is an origin. We can pick the origin anywhere we want. That's a degree of freedom. So let's choose a point along our road as our origin. The next thing to do is to choose an axis. Well, the road is naturally defining an axis for our problem, and so we'll call this the x-axis. Now, along with that axis, we want to divide that up into some type of units. So we might divide our axis like this. And what's important here is to introduce a positive coordinate direction. And so the way I'll do that is I'll call this the plus x. And on this side of the origin, x is negative. Now, the third most important thing is that we're going to talk about vectors in physics. So we want a choice of unit vector. Now, because it's only one-dimensional motion, we only need one unit vector. So what that means is a choice of a unit vector at every point. Let's just consider a point here, P1. So our unit vector, I'll call it I hat 1. Now let's pick another point here. We'll call this the point P2. And over here, we'll choose a unit vector I hat 2. So every single point in space has a unit vector. Now what's unique about this one-dimensional linear Cartesian coordinate system is the following. These unit vectors have the same magnitude. A unit vector, by definition, has magnitude 1. And they're pointing in the same direction. So if two vectors have the same magnitude and point in the same direction, they're equal. So what makes this coordinate system unique, this Cartesian coordinate system, that at every single point, no matter where we are, the unit vectors point in the positive direction. Because they have the same magnitude and direction, all of these unit vectors are equal, and we call that I hat. So symbolically, we may draw a picture and indicate our unit vector in the positive x direction. And this is our coordinate system, and we can next begin to describe the position and the velocity of our object as it's moving along this x direction. Now that we've chosen a coordinate system for our runner going along a road, we now want to describe the position function of that coordinate system with respect to our choice of origin. Now, the runner is a non-rigid object. Legs and arms are moving back and forth. So let's just imagine that there's some fixed point in the runner at the center. And let's give a vector. So we're going to draw a vector from above our origin to that point. And this is what we'll refer to as our position function. Now remember, every point here has an x coordinate. So we can now introduce our position function, which we'll call x of t, which is the coordinate location with respect to the origin. This is a function that will change in time. And our position vector is r of t equals the position function x of t. Now remember, this is a vector. The position function is just a quantity that's describing the location of this point with respect to the origin. But the unit vector is how we describe this as a vector. And so we write I hat. Now, x of t is what we call the component of the position vector. Remember, a vector has a component and a direction. And this the component is the position function, and that component, x of t, can be positive, as you see in this particular case. X of t can also be 0. That's if you're located at the origin. And if our runner is on the other side of the origin, x of t can be negative. So the component of the vector, of the position vector, can be positive, 0, or negative. And the direction of the position vector is the sign of the component times I hat. If the component is negative, then we have a negative I hat. The position vector is pointing backwards in the minus x direction. And if x of t is positive, positive I hat, position vector, as shown in this particular case, is in the positive I hat direction. So that's our first vector, the position vector in one-dimensional motion. Now that we've described the displacement of our object, remember that our displacement vector, delta r, in this time interval was x of t plus t minus x of t I hat, which we denoted as delta x I hat. Now let's just remind ourselves that this distance here, that's delta x, and this whole distance from here over to there, that's what we mean by x of t plus delta t. And now what we'd like to do is describe what we call average velocity. And our average velocity depends on our time interval. So this is for the time interval t to t plus delta t, while the person has displaced a certain amount of vector delta r. And our definition for v average, it's a vector quantity, so we'll write v average. We'll use 3 bars to indicate a definition. It is the displacement during a time interval delta t. So as a vector, we have delta x over delta t I hat. And this component here is what we call the component of the average velocity. So this is the component of the average velocity. And again, as before, this component can be positive, 0, or negative, depending on the sign of delta x. And the key point here is that average velocity depends on whatever time interval you're referring to. So that's our definition of average velocity. And now what we want to do is consider what happens in the limit as delta t becomes smaller and smaller and smaller. And that will enable us to introduce our concept of instantaneous velocity. We've now described what we call the average velocity for a time interval between when the runner started at time t to a later time at t plus delta t. And we describe that as the component of the displacement vector divided by the time interval times a unit vector I hat. Now what we'd like to ask a separate question. So our question now is, what do we mean by the velocity at some specific time t1? Now, in order to understand that, let's just make a plot of the position function. So remember, we called the component of the position function x of t. So we're going to plot the component of the position function with respect to time. Now, let's just say that the runner started at the origin at time equals 0, so I can make some type of arbitrary plot of that position function. And let's indicate in particular the time t1. So what this represents is x of t1. And so first I'd like to consider the interval t1 and t1 plus some later time delta t. So let's make this t1 plus delta t. This is the time delta t. And up here, we have our position function at t1 plus delta t. Then for this time interval, the average velocity, so for this particular time interval, v average represents delta x over delta t. So it's just the rise over run. It's just the slope of this straight line. So for this particular interval, the average is the slope of the line shown here on the figure. Now, this is just an average velocity, and now we would like to do is shrink down our interval delta t. So now let's make another case where we shrink delta t, and let's again calculate the average velocity. So for instance, suppose we have a smaller delta t, and we draw that line. Then our average velocity represents that slope. And again, we keep on taking a limit. So now we have another slope. So we have one slope, two slopes. And now we shrink again to a new delta t. And you can see that the slope is changing. And if we consider the limit as delta t goes to 0 of this sequence of slopes, then what are we getting? You can see graphically that eventually we will get to a line which is the slope of the tangent line at time t1. And so in this particular case, what we mean by the instantaneous velocity v at time t1 is the limit as delta x goes to 0, I hat here, where we're taking, this is the limit, delta t goes to 0, of x at t1 plus delta t minus x1 of t divided by delta t, and the whole thing is a vector I hat. So what a limit is a sequence of numbers. So we take a fixed delta t, we calculate the slope. We take a smaller delta t, calculate the slope. And each time we do that, the slopes represent a sequence of numbers, and the limit of that sequence, you can see graphically, is the slope of the tangent line at time t1. And so what we say is v of t1 is the instantaneous velocity at time t equals t1. And that's how we describe instantaneous velocity at some specific time. If we were now being a little bit more general, we could just say that v at any time t is the limit delta t goes to 0, delta x over delta t, all direction I hat. And the only thing here is we're no longer considering t1, but an arbitrary time t. This quantity, the limit, is awkward to write every time. It has a name, and that's precisely what we call the derivative of the position function. So our instantaneous velocity is the time derivative of the position function at any instant in time.
Go ahead.
Let's consider a one-dimensional motion that has a non-uniform acceleration. What we'd like to do is explore how do you differentiate position functions to get velocity functions to get acceleration function. So what we're going to consider is a rocket. So I'm going to choose a coordinate system y, and here's my rocket, and I have a function y of t, and I'll have a j hat direction, but this will be a one-dimensional motion. Now, I want to express, while the rocket is thrusting upwards and the engine is burning, we can describe a function y of t to be equal to 1/2 a constant a naught minus the gravitational acceleration times t squared. And we're going to have a separate term here, which is minus 1 over 30. And you'll see where this 30 comes in as we start to differentiate. The same constant a naught t to the 6th over t naught to the 4th. Now in this expression, a naught is bigger than g. And also, this is only true, this holds for the time interval 0, less than or equal to t, less than t naught. And at time t equals to t naught, the engine shuts off. And at that moment, our expectation will be that the y component of the acceleration should just be minus g for t greater than t naught. So now let's calculate the acceleration as the velocity and the position as functions of time. So the velocity, in each case, we're going to use the polynomial rule. So the y component of the velocity is just the derivative of t squared, which is just 2t. And so we get a naught minus g times t. And when we differentiate t to the 6th, the 6 over 30 gives us a factor of 1 over 5. So we have minus 1 over 5 times a naught t to the 5th over t naught to the 4th. And this is a combination of a linear term and a term that is decreasing by this t to the 5th factor. And finally, we now take the next derivative, a y of t, which is d vy dt. I'll just keep functions of t, but we don't really need that. And when we differentiate here, we get a naught minus g. Now you see the 5s are canceling, and we have minus a naught t to the 4th over t naught to the 4th. Now, at time t equals t naught, what do we have? Well, ay at t equals t naught. This is just a factor minus a naught. Those cancel, and we get minus g, which is what we expected.